on C of rank n and degree d. And then inside here, we can consider the stack bun nd of now vector bundles of the same rank. And let me just say what the relation of these stacks is to their moduli spaces. So if we look at the stack of all vector bundles, then it has the hard and narrow Siemens stratification. So you can write this as the semi-stable ones, and then union all different hard and narrow Siemens types. And then this semi-stable stack is actually, oh, do we have colored chalk? Yes. So then this semi-stable stack, oh, it looks like it's orange, but it's actually white. Maybe this one is, okay. The semi-stable stack is a, well, it maps to this, the moduli space of semi-stable vector bundles. And this is actually the good moduli space of this stack. And in the case when the rank and the degree are co-prime, which isn't the case that we're considering today, we're considering any rank or degree, but if that was the case, then this would be a GM job. Okay. So yes, as I said, I'm a bit out of touch with Blackboard talk, so I'm going to just write the theorem now, and then we'll see how much we get to talk about the proof. So the main theorem has 3 parts. So in Flag-Quot's triangulated category of motifs over K with Q coefficients, we have the following formulae. So firstly, for the stack of torsion sheaves. So here the rank is 0. This is the d-symmetric power of the motif of C crossed by BGM. And this thing here is actually just a motif of the stack of degree 1 torsion sheaves. And then now let's consider the motif of the stack of vector bundles. Then that's the symmetric algebra on now the motif of C crossed by Pn minus 1. So maybe I'll write out what that is. So that's the motif of BGM tensor by the motif of the Jacobian of C, and then tensor by, and then we've got some zeta functions. So I will write out what these are in a minute, so there's going to be more in the next formula. And then the third part of the theorem is about the stack of coherent sheaves. And now this is the symmetric algebra on MC crossed by BGM. Oh, sorry, I realized there should be a reduced here, and same here. So you remove a copy of Q0. And so then I can also write this, I can expand this out, and this is the motif of BGM. Tensor the motif of Jacobian. And now I've got an infinite tensor product here of zeta functions of the curve. And so let me write out what these are and also explain this notation. So this for me is the Tate twist. Maybe I can write that here. So everything is pure. So I just write the Tate twist Qi, 2i, always with this curve brackets, just because we're only ever going to see pure Tate twists. Yeah, so let me write out the zeta function. So this is the sum J, and then we take motifs of symmetric powers of the curve. And then different Tate twists here. So that's an IJ. Yeah, so what can I say about this before we get into the proof? So firstly, everything is generated by the motif of the curve. So everything can be written in terms of the motif of the curve. So for example, we have Jacobian symmetric powers of curves appearing, but it's all lies in the category generated by the motif of the curve. And everything is pure. And what I guess you could say in genus 0, then actually it's also of Tate type. But otherwise, once we go into positive genus, then we see that it's no longer a Tate type, but it's still quite simple. It's just generated by the motif of the curve. Okay. And oh yes, while we're at it, let me just say on the level of cohomology, these results were known by, so firstly, Le Mans described this one on the level of cohomology. Then I guess the stack of vector bundles was kind of described by Hardenara-Thiemann and Atiyah-Bott. And then the stack of coherent sheaves on the level of cohomology was described by Heinlott. Okay. I'll try and leave that up. I don't know what people can see, but okay. Yeah, let me say a few words on motifs of stacks. I just want to be brief. So because I think you could spend a whole talk on motifs of stacks. So for a quotient stack, Totaro defined the motif using a sort of algebraic Borel construction. And then if we're working with a Tal motif, so well, we're always considering rational coefficients anyway. So let me just write a Tal motifs here. There are several different things that you can do. So you can take a checked hypercover associated to an atlas and use this to define the motion of the stack. And you can also do a nerve construction. And then, so I guess maybe later this week, Timo will talk about this, but there's a much more general construction, which also has some of the operations. So somehow you, yeah, maybe let me just say, well, I don't want to say too much, but essentially you just consider maps into your stack from affine schemes. Okay. Oh yes, and maybe I should say as well that Simon and I generalized this construction of Totaro to something called a exhaustive stack. So I'm not going to get into the definition. But again, it's somehow approximating your stack by schemes, I guess. Okay. Yeah, let me check the time. Okay, good. Yes. Approximating them by smooth projective schemes? No. So just finite type separated schemes. So just things that you can define the motif of. So although actually, well, so in our case, I think they're smooth, the things that we approximate them by, but you, so actually, I guess, yeah. So we actually only show that this is well defined in the case when the stack is smooth. So yeah, I'm not going to give the definition because it's long and sorry. I can tell you afterwards a little bit about it.
But I mean, are these all different descriptions of the same category of motifs or all variants?
So these all give the same definition when you're working with Q coefficients. So actually the Totaro definition also works with Z coefficients, so with Nistovich motifs. And also this one about exhaustive stacks does as well. So whereas these, I mean, they're all suited to a Tal motifs. Okay. But yeah, so they all agree if you're working with the Tal motifs, which is what we are. Okay, so the first part is going to be about torsion sheaves. Yes, and so this goes back to Le Mans, like I said. And so hopefully this story is familiar to many people in the room. So if you consider the stack of degree D torsion sheaves, then actually you can sort of instead filter these torsion sheaves. And let me now write this with a tilde. And so now we're considering filtrations where the degree of each Ti is I. And this map pi is a small map and a oh, was that something or no? No, I'm not sure. And a principal SD bundle over the open set in here, where the support consists of distinct points. Okay, and in particular, if X is A1, then you can actually identify this with the Grothendieck-Springer resolution. Okay, and so then on the level of cohomology, because this map pi is small, this tells us that the rational cohomology of the stack of degree D torsion sheaves, oh yeah, let me write the Q in. That's important that we're working with Q coefficients here, is the SD equivariant part of this thing here. Sorry, the SD invariant part. And then now we just need to compute what this is, but then we have an associated graded map. So we have a map group going to a product of stacks of coherent sheaves of torsion sheaves of degree 1. And this is an iteration of vector bundle stacks. So I'm also not going to give the definition of what this vector bundle stack is, but what you should think about it is being as like the quotient of two vector bundles. So here it's going to be an X quotiented by a Hom thing. Oh yeah, so that's going to be the so you're now looking at flags inside here as well. So it's just the usual thing, like for n and n tilde, but tilde. So it's like extending the usual Springer resolution, the Grothendieck one. Okay. Okay.
Question about the base field.
Yeah, it's just any field. Okay. Yes, and so just let's complete this cohomological picture. So then in particular, the fibers of this are contractible. And so then we get that the cohomology of the stack of degree D torsion sheaves, so maybe I'm now going to start omitting the Q because it's always Q coefficients, is then just the, SD invariant piece of, and then we have the cohomology of a product of stacks of torsion sheaves of degree 1. And so then this is just sim D of the cohomology of the stack of torsion sheaves of degree 1. So now let's talk about on the level of motifs. Well, so following De Cataldo and Migliorini, we give a motivic description of small maps where on a dense open, they become a principal G bundle. So let me state the theorem. And I'm going to give this a name because we're going to use it later. So let's call it theorem A. So for a small proper map, f from x to y of smooth stacks whose restriction to a dense open and is a G-torser, then so then G obviously acts on x0 and its motive, but this action actually extends to the motive of x. So then the G action extends to the motive of x. And again, we're working with rational coefficients, so we can define the G invariant part. And this is actually isomorphic to the motive of y. So maybe I should really emphasize the rational coefficients here. Okay.
For finite group G, or for any G.
Well, it has to be finite, right? Because yeah, yes, yeah. Indeed, I mean, you need to define this, you need to divide by the order of the group. Okay, and then the other proposition that I wanted to state is just about vector bundle stacks. So for a vector bundle stack, E over X, i.e., let me just say what I mean by this, i.e. there exists vector bundles with a homomorphism between them. Such that E is the quotient of these. We have that the motive of E is the same as the motive of X. Okay, and let me so this is, let me just, since the proof is 2 lines, I can write it. So we claim that if we work in the relative to the stack X, then if we look at the motive of this map here, then we get a map to, let me call it 1x. So the unit in here, and we claim that this is an isomorphism. So, and to show this, it suffices to check on points. By pulling back. But then when we pull back, then EX then just becomes a quotient of 2 vector spaces. And so then it just looks like A to the R crossed by BGA to the S, let's say. And so then in particular, its motive is trivial. So then in the it's over the residue field of X. Okay. And then using theorem A and this proposition, you basically, so it's already gone, but you get part 1 of our theorem. So as a corollary, you then get that the motive of the stack of torsion sheaves of degree D is then the D-symmetric power of the motive of the stack of coherent sheaves of torsion sheaves again of degree 1, and then this is just a GM gerb over the curve. So this is then the motive of C cross BGM. Okay. Yeah.
So did you use that you have a rational point?
Not in here. No. It's coming in part 2. Yeah. So part 2 is an older result, which is already published. So I should say part 1 and 3 are not even on the archive, but hopefully they will be soon. So let me now talk about part 2, which is the stack of vector bundles. Yeah, probably this way is better. Okay. So now we're going to use the fact that we've got this rational point. So now we let x be a rational point on our curve. And we're going to use this rational point to rigidify the stack of vector bundles. So we're going to rigidify using certain Flag-Quot schemes. So actually the history of this is that we first tried to rigidify using Quot schemes, and that wasn't enough. So then we actually considered Flag-Quot schemes. So let me introduce first the Quot scheme and then the Flag version. So we consider what we call div L to be the set of subsheaves E inside OLX plus N of the same. So E should have the correct invariance. So the rank of E should be N, and the degree of E should be D. And so in particular, this quotient is going to be a torsion sheaf. And this is a smooth projective Quot scheme. And then we can further rigidify by looking at a Flag version of this, which now, actually the degree of the torsion thing is going to be, well, NL minus D. And so now we sort of filter this in NL minus D steps. So let me write that out. Such that, okay, the rank of each EI should always be N, and the degree of each EI should be, I've got D plus I, yes, that makes sense, okay. Yes, yeah. Okay. And again, this map is also a small map, and now a principal SNL minus D bundle on the open where the support is of the torsion thing consists of distinct points. And so theorem A, again, tells us that we can compute the motif of div L in terms of the motif of F div L. So it's just the F and L minus D invariant piece of the motif of F div L. And then what's the motif of F div L? Well, I have not left enough space, but there's a map, which we're going to call the support map, going from here to C to the NL minus D, just looking at the support of the degree 1 torsion sheaf in each successive quotient here. And this support map is actually a iteration of projective bundles. Essentially, you're doing a length 1 Hecke modification at each step. And so this part here, so before taking the invariant piece, this is just actually the motif of C crossed by Pn minus 1 to the N NL minus D. So it's actually an NL minus D iterated Pn minus 1 bundle. And so then we get that this is then the the sim NL minus D of, and then the motif of C crossed by Pn minus 1. And so how is this now related to the stack of vector bundles? Oh, sorry, now I'm going to have to push this down. So we have these rigidifications. So firstly, from this in scheme of these quot schemes div L, we have a forgetful map which just sends this pair to E itself. And then we also have the forgetful map from the Flag-Quot schemes. I should say the Flag-Quot schemes are also smooth projective. Oh, sorry, wrong way. This one here is almost a vector bundle. So it's enough that actually the motifs of these two coincide. So the motif of burn is then the homotopy colimit of the motifs of the div Ls. And then we can now, so actually the problem was that at first we just did this, but we couldn't understand on the level of motifs these transition maps very easily. But we can after we replace them by these Flag-Quot schemes. So yeah. So I guess I should maybe I should say that at this point this is actually true with Z coefficients. Actually, you didn't need to assume the rational point here. So you could have actually replaced instead of X, you could have just looked at a divisor and done something similar. Okay. So some other effective divisor. So now let's give the proof of the formula. So I think it's better if I have a new board because I'm going to draw a big diagram.
Well, probably I missed it, but L is large enough so that there's no X to Y.
Well, so anyway, it doesn't matter what small L is here, right? I mean, once we get this. But yeah, in this almost a vector bundle, you sort of take, yeah. So yeah, you somehow take some open part of the stack on which you get a sign which is almost a vector bundle over it, and so the X ones vanish there. So I mean, maybe the best way to say it is that div L is sort of an open thing inside a vector bundle on some open part of burn, and then it's getting sort of bigger and bigger, this approximation. Okay. So then for all L, we have a commutative diagram. And so for simplicity, I'm just going to let D be equal to 0. This is just because otherwise I have to write minus D everywhere. So it's just to, it's really just for simplicity. And so I just don't have to carry around the D factor everywhere, but it's in the paper we do it with all D, so don't worry. So we have these maps, these immersions from div L into L plus 1. Let me call this IL. And then now we have the flag versions of these quot schemes. And I'll tell you what the map JL is in a minute. And then we have the support map here going to C to the NL. And the same support map here going to C to the NL plus 1. And then let's also now project from NL copies of C crossed by Pn minus 1. And so this map is going to be, so our given point X that we fixed all along. So we take X n times and then we take the identity. And then here I'm going to take X and I'm just going to choose a random point on Pn minus 1 and take that n times and then the identity on the other factors. And let me call this map, so I think I need a name for this. Yeah, let me call it AL. So the JL are determined by a choice of flag, basically between OC plus N and OCX plus N. And the P is just also you choose a point P in Pn minus 1. So on the level of motifs, actually, these choices aren't going to matter. So they're going to induce the same maps on the level of motifs. So then this induces commutative diagrams. On the level of motifs. So actually, we're just going to compare these two to start off with. So from M of F div L to M F div L plus 1. And then we've already seen that the motif of F div L was just the NL tensor power of the motif of C crossed by Pn minus 1. So I'm going to introduce some notation for that. So let me write M Cn for the motif of C crossed by Pn minus 1. Then it's MCn NL times, and this is MCn NL plus 1 times. And we get a map like this, where this is the motif of the map JL, and this here is the motif of the map AL. And then taking the invariant pieces with respect to the symmetric groups here, we then get the motif of div L maps the motif of div L plus 1. And this is now the NL symmetric power of this motif MCN. And now let's write this as Q0 plus the reduced motif of C crossed by Pn minus 1. And so then this becomes the sum from I equals 0 to NL of sim I of MCN bar. And this is the same thing, but now we're going to NL plus 1. And this is actually just the obvious inclusion here. So now we've actually really described what this transition map is. So it's just the inclusion of the first NL factors into this larger direct sum. And so then, yeah, I'm probably going to need more space. Okay, I'll start here. The motif of Bun ND was, remember, just the homotopy colimit of these div L's. But then that's just the homotopy colimit of these things, just including each other in the natural way. And so indeed, this is the symmetric algebra on the reduced motif of C crossed by Pn minus 1. Okay, and then basically just expanding out what are the factors here, you get the expression in terms of the Jacobian and BGM and these zeta functions. Okay, let me see how much time we have. So 10 minutes or a little bit less, yeah. Okay, so then I think we can talk about coherent sheaves. And so maybe let me just say that although we assume D is equal to 0 here, we would just have had a minus D here and a minus D here, and you wouldn't see this. So actually, the thing that you get doesn't depend on the degree. And in the case of coherent sheaves, it doesn't depend on either the degree or the rank. So this is quite surprising, I guess. So now we're considering coherent sheaves of positive rank. So let M be positive because we've already done the torsion sheaves. Then every coherent sheaf has a torsion filtration. Which let me write like this. So the torsion part of E sits inside E, and then we get this quotient being the free part. So this is a vector bundle. And this gives rise to a torsion stratification of the stack of rank n degree D torsion sheaves. So over E greater than or equal to 0, where here E is the degree of the torsion part of each sheaf. And then again, we have this associated graded map. Taking this filtration to these two things here, which then lands in, so firstly we have degree E torsion sheaf, so this part, and then a vector bundle of rank n and degree D minus E. And this associated graded map is again a vector bundle stack. So the motif of each of these pieces is just the motif of these two things, which we know from parts 1 and 2. So remember, this actually doesn't depend on the degree here, it just depends on this n, the motif. Okay, and then we look at the Giesen sequences associated to this stratification. So the open and closed pair given by, so we look at things which have exactly degree E torsion, and then that sits inside the things with less than or equal to degree E torsion as the closed part, and then the open part is where it's strictly less than E. And so this induces a triangle for us, going from the motif of this open piece, then to the motif of this, and then the Gaussian map, and we have a twist by the codimension, which is just NE. Which I claim splits and so for this, the point is that I should say splits inductively. So we know that the motif of this thing is pure, and inductively you also know that the motif of this thing is pure, and so then you're going to see that this this map here has to be 0. So the Homs from here to this shifted by 1 have to be 0 by purity of these things. And so then what we get is, so yeah, let's now put this all together. So then we get that the motif of, so all of these different triangles splits, then the motif of the stack of rank n degree D coherent sheaves is just the direct sum of the motifs of each of these pieces with various tape twists. And then each of these pieces, we've calculated what they are. So now we get the motif of the stack of degree E torsion sheaves, tensor with the motif of bun. So let me just write bun n because the D doesn't actually matter in the formulae. Oh, I'm sorry, so there should be an NE here. Yeah, and then if you pull this bit out, so I think that's the easiest way to do it. So then this is then the motif of bun n tensor, and then the sum of it or E greater than or equal to 0. And remember that this is the ETH symmetric power of the motif of C crossed by BGM. And I'm going to actually integrate this tape twist into this. So let me write this as sim E of, and then the motif of C twisted by N tensor the motif of BGM. I think I need another bracket. Okay, and then what is this whole thing? well, then this is just the tensor product from k greater than or equal to n of the zeta function of C with coefficient the k tape twist. And so then if you put this all together, then you get that this is the motif of BGM, tensor the motif of the Jacobian of C. Tensor, so then this is the sum of the first n-1 tape twist, and then we've got the other ones here. So sorry, the zeta functions for the first n-1 tape twist, and then we've got the other ones here. And so that gives the formula for the stack of coherent sheaves on a curve. Okay, thank you very much for listening.